Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd edition by Briggs, Cochran, and Gillette. This video is going to focus on the power rule, and the power rule is the thing that's going to make taking derivatives 800 times easier. I am hoping that as you have been practicing in 3.1 and 3.2, you have started to notice a pattern of when I take the derivative of polynomials, and that pattern is going to come to fruition today. So what I'm going to start with is I have two equations here I want to look at. I've got y equals 2x plus 3. I also have y equals x squared. And what I'm going to do is I'm going to take the derivative of both using the method we have, and I want to start developing a pattern. So I'm looking at this. The derivative of this is the limit as h goes to 0 of, and I'm going to skip a step, just not writing it out again. So 2 times x plus h plus 3 minus 2x plus 3. I actually did this in this exact equation in our derivative as an operator video, and that's all over h. Well, distributing out that 2, and I'm going to go and distribute this negative here, or this subtraction through, so I've got 2x plus 2h plus 3 minus 2x minus 3, all of that over h, and we're going to play the what cancels game, so 2x and negative 2x, 3, negative 3 cancel, and I am left with the limit as h goes to 0 of 2h over h. I'm dealing with a limit, which means I could pretend that h over h cancels, leaving me with the limit as h goes to 0 of 2, which is simply 2. Now, we talked about in our very first derivative video that the slope of the tangent line is dy dx, and the slope of this linear equation is the rate of change for every point on there, so it's always 2. So really nice things. If I just have a line, we've kind of hinted at this before, it's just the slope of the line. And we're going to see, I think we're going to see this better here in a minute. What I want to notice is, number one, the derivative of a constant is always 0, and we're going to get into that more when we do our summation video. But what I really want to emphasize is, hey, look, let's look at this 2x term. The x kind of goes away, and I'm just left with a slope. And I really want to focus on that as we do x squared. So let's go ahead and do the derivative of x squared. So that's the limit as h goes to 0 of x plus h squared minus x squared over h. X plus h squared is x squared plus 2xh plus h squared. I'm going to subtract x squared still, all of that over h. Now, x squared minus x squared is 0. Limit h goes to 0 of 2xh plus h squared over h is the same as the limit as h goes to 0 of h times 2x plus h all over h. And once again, we're dealing with a limit here, so I can go ahead, cancel out h over h, even though I'm evaluating when h is 0, giving me that that's the limit h goes to 0 of 2x plus h. So here this is a polynomial, I can just plug it in, h is 0, so I've got 2x plus 0, which is just 2x. Now, something weird's going on. The fact that really, if I take x squared, what's really happened is this 2 became the coefficient in front, and I said 2 minus 1, which is just 1. Now, maybe this is just something weird going on with these two particulars. They're very, very small degree polynomials. So let's go ahead and amp it up one more time to, let's do y equals x cubed. Okay, so that one's pretty straightforward. So I want dy dx, so that's the limit as h goes to 0, x plus h cubed minus x cubed over h. Through the binomial theorem, I've got x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Well, looky here. Cancels. So far so good. And I'm going to go ahead and take that step where I factor out the h before I do anything. Limit h goes to 0 of h times 3x squared plus 3xh plus h squared over h, taking the limit so I can get rid of the h's, leaving me with the limit h goes to 0, 3x squared plus 3xh plus h squared equals, plug in h's for all my, or plug in 0 for all the h's, so I've got 3x squared plus 3x times 0 plus 0 squared. Now those last two terms are 0. 3x squared. And we go back to that weird pattern I just said. Sorry. The derivative of x cubed is 3x squared. So I started with x cubed. The exponent, sorry, my math just failed me, becomes the coefficient, and I take 1 from the exponent, so that gives me 3x squared. And that's the magic of polynomials, is there's this thing called the power rule. And here's how I'm going to write the power rule. It's slightly different from the textbook. And I'm going to say for n not equal to 0, so for any exponent that is not 0, then the derivative of any x to some power is that power times x to the n minus 1. And this is the new normal for taking derivatives. I never, I'll be honest, there's a good shot on a midterm or something I might ask you to work it out by hand or do something like that. But that's because I want to make sure you understand where all this stuff comes from. But when you're taking a derivative from here on out, the big idea is, hey look, the exponent becomes the coefficient, take 1 from the exponent. So a couple quick examples of this, just to emphasize how easy this is. Before I go too far, I do actually want to talk about what happens when the exponent is 0, because I think that is important for us to see. So this example, which I think is somewhere around the neighborhood of example 4, is going to be, I want d dx of 3. So just the number 3. Now, I'm going to be spiffy here, and I'm going to write that's d dx of x to the 0, and because anything to the 0 power is wow. That's d dx of 3 times x to the 0. And I can say x to the 0 because anything to the 0 power is 1 except for 0 to 0, and we're just gonna deal only with limits here, so it's okay. Now, what does this mean? Well, if I play this game, I should be able to say, well then that would be 0. It says 0. Actually, I take this back. This totally works for 0. Look at me. I'm learning something today. I'd never thought about it like this. Let's just follow our rules. So that would be, I'm going to take the exponent and multiply it by 3 times x to the 0 minus 1. Now, if I'm careful here, well, that's just 0. I have always thought about this slightly differently. What I've always thought about is if I graph this function like this, well, if this is 3, so this is y equals 3, what's the slope of that line? Well, it's 0 because it's a flat horizontal line, perfectly perpendicular or perfectly parallel to the x-axis. So actually talking about it like this, we're okay. So I'm actually going to come in here and I'm going to abridge my rule, and I'm going to say for any integer n. Now your book says non-negative integers, and I disagree with that, and we're going to see that as we move forward going into more complicated derivatives, that this rule actually still works for negative integers. But for today, the big idea I want to focus on is, hey look, the power rule is fantastic. All we're doing, if I've got f of x equals x to the 7th, then the derivative, so the derivative of f with respect to x, and I'm starting to use that terminology, please note, the derivative of f with respect to x is 7x to the 6th. If f of x is x to the 1,000 power, it's just ridiculously huge polynomial, well, the derivative of f with respect to x is 1,000 x to the 999. The power rule is that simple, and I hope that you have enjoyed me significantly simplifying polynomial derivatives. Hope you found this video useful, especially with me apparently teaching myself something, or I guess I knew that, but it was one of those where I thought about it in a new way and I really liked it. So best wishes. I hope you found the video useful, and good luck in this semester.